Hello everyone, in this video I am going to explain stereoisomerism. So in isomerism there are two types, broad classification. One is structural isomerism, other is stereoisomerism. Structural isomerism completed in my previous videos: chain isomerism, position isomerism, functional group isomerism, metamerism, ring chain isomerism and tautomerism. All are completed. This is other wing, stereoisomerism. So what are stereoisomers? Two or more molecules which have same molecular formula and same bonding arrangement between atoms. Bonding arrangement also same. Whereas in structural isomers, bonding arrangement is different. But in stereoisomers, molecular formula same, bonding arrangement is also same. But only difference is they are differ by spatial arrangement of atoms. Spatial arrangement difference. Bonding arrangement same, molecular formula same, spatial arrangement of atoms different. Such molecules are called stereoisomers, and the phenomena of existing stereoisomers by organic molecules said to be stereoisomerism. Stereoisomerism is mainly two types: conformational isomerism and configurational isomerism. In this video I will explain conformational isomerism. So see definition: two or more molecules which have same molecular formula, same bonding arrangement between atoms but differ by spatial arrangement of atoms or groups said to be stereoisomer, and the phenomena of existing stereoisomers by organic compounds said to be stereoisomerism. Example, see example. So for these two, molecular formula same. Here blue dot is carbon atom, and red circle is also carbon atom. There are two carbon atom. One has taken with small size, other taken with large size. So here blue dot carbon with 3 hydrogen, red circle carbon with 3 hydrogen. Two carbons with 6 hydrogen, ethane molecule. So here when you compare these two, here carbon atom, red circle carbon atom with 3 hydrogen, blue dot carbon with 3 hydrogen, same. Molecular arrangement is same, but spatial arrangement different. Okay, molecular formula same but spatial arrangement is different. So here bonding arrangement same between carbon and hydrogen only, but this arrangement of this carbon is here. Spatial arrangement is different. Bonding arrangement same. Here bond between carbon and hydrogen only, here bond between carbon and hydrogen only. Bonding arrangement is same but spatial arrangement different. It by the rotation bond, this comes to here, it comes to here, it comes to here. This is spatial arrangement difference. When you compare here, second example for stereoisomerism. See here carbon chlorine bond, but arrangement different. Here it is here two chlorine atoms in one direction, downward direction. Here two chlorine atoms opposite direction. One is pointing upward, other is pointing downward. Bonding between atoms is same. Here bonding arrangement same, molecular formula same, two carbon, two hydrogen, two chlorine, molecular formula same. Bonding arrangement same, carbon chlorine bonds, carbon hydrogen bonds. Bonding arrangement is also same, but next for this molecule, CH2OH same, CHO same, OH same, HH same, molecular formula same. Bonding arrangement also same, but here OH right side, OH left side. Arrangement is different. Such isomers, spatial arrangement different. Such isomers are called stereoisomers, and the phenomenon is called stereoisomerism. Here it comes under conformational isomerism, and it comes under geometrical isomerism. Okay, so stereoisomerism. In stereoisomers, first one, conformational isomers. What are conformational isomers? Different arrangement of atoms in the space, which arises from rotation of carbon-carbon single bond in alkanes. Generally alkanes show conformational isomerism. In alkanes there is a single bond between two carbon atoms. By the free rotation of carbon-carbon single bond, different arrangement of atoms are possible. Those different arrangement of molecules said to be conformers. Single molecule, by the rotation of carbon-carbon single bond in alkane, different spatial arrangements are possible. Each spatial arrangement is said to be a conformer. conformational isomer. Those are formed by the rotation of carbon-carbon single bond. So those are also called as rotational isomers, or other name is rotamers. Totally 4 names: conformational isomers, conformers, rotational isomers, rotamers. There are 4 names. So what are rotational isomers or rotamers, or conformational isomers or conformers? Different spatial arrangement of atoms which arises due to rotation of carbon-carbon single bond in alkanes are said to be conformational isomers. Okay, so rotation about of carbon-carbon single bond is not completely free. Of course, free rotation is possible, but not completely free. A little amount of energy, very little amount of energy. For 1 mole of molecules rotation, nearly 1 to 20 kilojoules of energy is required. Such energy, that little amount of energy, they can obtain from molecular collisions by the light. So very little amount of energy sufficient to rotation of single bond in alkanes. That's why alkanes show conformational isomerism. Conformational isomerism is also dynamic isomerism. Next, conformational isomerism denoted by 2 different projections. One is Sauer's projection, other is Newman projection. So I will take ethane molecule example. In ethane molecule, conformational isomerism, 2 different isomers. I will explain with Sauer's projection as well as Newman projection. Take this one. Now, conformational isomerism in ethane. Example ethane. Ethane formula C2H6. Ethane, eth plus ene. 2 carbon atom, there is a single bond between them. Carbon atom, between carbon and carbon, single bond. Each carbon contains 3 hydrogen atom. Saturated carbon. Okay, here this bond is freely rotate about of its axis. It is freely rotatable. So free rotation is possible about that axis. If double bond is formed between 2 carbon atoms, free rotation is not possible. Because, so you know, sigma and pi bond, understand the nature of sigma and pi bond. Sigma bond is formed by linear overlapping of atomic orbital. Here overlapping, linear, axial overlapping between 2 atoms, between 2 carbon atom, or any. Sigma bond is formed by axial overlapping of atomic orbital. So about this sigma bond, free rotation is possible like this. But if you take pi bond is formed by sidewise overlapping. So sidewise overlapping of atomic orbital or hybrid orbital. Whenever sideway along with sigma overlapping, if pi overlapping is also present, then rotation is not possible. If carbon-carbon double bond, free rotation is not possible. But here single bond, only sigma overlapping, free rotation is possible. Hope you understood. So in ethane, by the rotation of carbon-carbon single bond, infinite number of conformational isomers are possible. By the rotation of carbon-carbon single bond in ethane, infinite number of conformational isomers are possible. By the rotation of carbon-carbon single bond in ethane, infinite number of conformers are possible. Infinite number of conformers are possible. By the rotation of carbon-carbon single bond in ethane, by rotation 1 degree, 1 isomer, 2 degrees, 2 isomer, for each degree 60 minutes, by the rotation of 1 minute, 1 isomer, for each minute 60 seconds, by the rotation of 1 second, 1 isomer. Thus, infinite number of conformational isomers are possible for ethane. So if molecule has 0 angle between 2 hydrogen bonds, 2 carbon hydrogen bond. If 1 second rotation 1 isomer, 1 degree rotation 1 isomer, 1 second rotation 1 isomer, thus for 360 degrees, 360 into 60 minutes into 60 seconds, for each fraction there is a conformational isomer. Thus ethane has infinite number of conformational isomers, but out of infinite number of conformers only 2 are important, out of which 2 are important, eclipsed conformer and staggered conformers. Eclipsed and staggered conformers are important. Except eclipsed and staggered conformers, remaining conformers are called, except these two remaining conformers are called skew conformers. Remaining all are in infinite number of conformers except eclipsed and staggered. Remaining all conformers are, they are not important, said to be skew conformers. Okay, first see eclipsed conformer and staggered conformer. I will show both. Staggered conformer, eclipsed and staggered conformer with Newman formula, Newman projection. According to Newman projection, 2 carbon atoms are denoted with front carbon denoted with A point. Front carbon contain 3 hydrogen atom. Rear carbon denoted with a circle. Rear carbon means back carbon. Okay, so this is what front carbon, and this circle is what back carbon or rear carbon, rear carbon. Front carbon, rear carbon. Front carbon and rear carbon. Okay, so for front carbon and rear carbon there are 3 hydrogen. For front carbon 3 hydrogen atom. I am taking this is front and this is rear, or any one is front, rear. So here this is front carbon that contain 3 hydrogen atom. Front carbon, rear carbon are aligned with each other. Rear carbon also contain, this is rear carbon that contain 3 hydrogen atom. Those 3 hydrogen atoms of rear carbon are exactly behind the hydrogen atoms of front carbon. Front carbon hydrogen atoms are with blue line. Now see rear carbon denoted with red circle and hydrogen atom. Rear carbon hydrogen atoms are exactly behind, directly behind the front carbon hydrogens. Such a conformer is called as eclipsed conformer. This is eclipsed conformer. By the rotation of bond between front carbon and rear carbon, by this rotation, so first alignment is like this, by the rotation of bond, by keeping one stable, I am rotating other. So if back carbon is rotating by 60 degrees, so from here to here what is angle? 360 angle. 360, 3 parts, 120, 120, 120. From here to here 120. If this hydrogen comes here, 60 degrees rotation. So from here to here 120, then half of this become, how much rotation? Half of this become 60 degrees rotation, carbon carbon single bond by rotation of 60 degrees. By rotation of 60 degrees, what will happen? So I am keeping front carbon constant, front carbon there only without change. Rear carbon rotation takes place, rear carbon here to here, here to here, here to here. Rear carbon comes here, this one comes here, and this one comes here. This is called staggered conformer. This is what? Staggered conformer. Eclipsed conformer, staggered conformer. In staggered conformer, the bond carbon-hydrogen bond of front carbon, CH bond of front carbon is exactly bisecting bond angle between two carbon. What is bond angle? Angle between two adjacent bonds. For rear carbon, these two are adjacent bonds. For rear carbon, these two are adjacent bonds. This is bond angle. Bond angle. Front carbon hydrogen bond is bisecting. Bisecting means making equal halves. Thus arrangement is present. Hydrogen atoms of front carbon are arranged in such a way the CH bond of front carbon bisecting bond angle of rear carbon, or CH bond of rear carbon bisecting the angle. So bond angle here, this is bond angle, this is bisecting here. Thus front carbon bonds bisecting rear carbon bond angle, rear carbon bonds bisecting front carbon bond angle. Thus arrangement is present, that is called as staggered conformer. Okay, so except these two, eclipsed and staggered conformer, remaining all are called skew conformers. Okay, when you see eclipsed and eclipsed conformer, in eclipsed conformer, bond pair of this bond and bond pair electrons of another carbon hydrogen bond are very close. They are very close. So but here front carbon hydrogen bond pair is far from rear carbon hydrogen bond pair. So bond pair repel with each other. Here due to close to each other, they are close to each other, here more repulsion. Repulsion is more bond pair repulsion, more BP repulsion. More BP repulsion. So bond pairs of same carbon, same angle, 120, 120, 120 only. I am talking about bond pair of one carbon with bond pair of other carbon. Here they are very close, so more repulsion. More repulsion means more energy. More repulsion means more energy. More energy means less stable. More energy means less stable. Here opposite. What do you say? Here bond pairs are far from each other, so less bond pair repulsion. Here less BP repulsion. Bond pair repulsion. Front carbon CH bonds, rear carbon CH bonds far from each other, less repulsion. Less repulsion in this sense, less energy. Less energetic. It is less energy. Less energetic means more stable. Less energetic species are more stable. That means in conformers of ethane, staggered conformer is very stable because of less repulsion. Due to this repulsion, eclipsed form it changes to staggered form because bond pair repulsion. So this bond pair repulsion, which results rotation of carbon single bond, is called torsion strain. The bond pair repulsion which results rotation of carbon single bond is called as torsion strain. So this is Newman projection for eclipsed staggered conformer. Next, take this one. I will show Sahar's projection for eclipsed staggered conformations. Eclipsed conformer is more energetic, less stable. Staggered conformer is less energetic and more stable. The energy difference between them is 12.5 kilojoules per mole. Right, see, Sahar's projection. In Sahar's projection, front carbon denoted with blue dot and rear carbon denoted with red dot. A bond between them denoted with a line which is slightly tilted towards right. Okay. The front carbon contain how many hydrogen? 3 hydrogen. 1, 2, 3. And rear carbon also contain 3 hydrogen. So this is rear carbon contain 3 hydrogen. Front carbon 3 hydrogen, rear carbon 3 hydrogen. Rear carbon also contain 3 hydrogen. Front carbon CH bonds are exactly aligned with rear carbon CH bonds. Thus this become eclipsed conformer. By the rotation of bond, this bond, carbon-carbon bond, what happened? By the rotation of bond by how much angle? 60 degrees rotation. Carbon-carbon bond, how much rotation? 60 degrees rotation. By this rotation, what we get? Your keep one bond constant, carbon-hydrogen bond is front carbon-hydrogen bonds are constant. I am changing rear carbon hydrogen. So actually it comes here exactly opposite it by the rotation of 60 degrees it comes here. It comes to in middle means comes here, and this one comes to here. This one comes to here means like this. Okay, here if you see this bond CH bond bisecting angle between these two are not. If you view here, so this is bond angle of rear carbon, front carbon CH bond bisecting rear carbon bond angle. Thus this becomes staggered conformer. Eclipsed and staggered conformers. So staggered conformer is more stable, eclipsed conformer is less stable. If you see energy and angle between front carbon CH bond and rear carbon CH bond is said to be dihedral angle. So angle between front carbon CH bond and rear carbon CH bond. So see here, if imagine this bond come present here in the same line, this angle is called as dihedral angle, or otherwise in Newman projection formula I will show this is front carbon hydrogen bond and this is front carbon hydrogen bond and this is rear carbon hydrogen bond. Front carbon hydrogen bond, rear carbon hydrogen bond. This bond is said to be dihedral angle. Dihedral angle is denoted with pi. Dihedral angle denoted with pi. Okay. So if you see a plot between dihedral angle and energy, here first 0 dihedral angle on x-axis, energy on y-axis. So here eclipsed conformer 0 degrees dihedral angle, that means eclipsed form, and 60 degrees dihedral angle, 120 degrees dihedral angle, 180 degrees dihedral angle, and the next 60, 240 degrees dihedral angle, 300 degrees dihedral angle, and finally 360 degrees dihedral angle. So with eclipsed conform 0 degrees dihedral angle, eclipsed form more energetic, and 60 degrees less energetic. Next again with 60 degrees eclipsed form, 180 staggered form, 240 eclipsed form, 300 staggered form, 360 eclipsed form. So here 0 degrees angle means eclipsed form. Here 60 degrees dihedral angle means that is what? Staggered form. This is staggered form. 120 degrees angle. So from here if it comes to here. So if you understand clearly, so this is first form. From eclipsed form 0 angle eclipsed form 0 angle. If it comes to 120 angle, it comes here. This hydrogen comes here. This hydrogen comes here. Same or not? Same eclipsed again. By 60 degrees we get staggered. By 120 degrees we get again eclipsed one. Okay. So by 120 degrees rotation, eclipsed one. Eclipsed one. By 240 degrees eclipsed one. 360 degrees eclipsed one. 60 staggered. 180 staggered and 300 also staggered. If you see energy gap between them, this is more energetic and this is less energetic. This is energy barrier. The energy between them is 12.5 kilojoules per mole. 12.5 kilojoules per mole. Okay. Hope you understood. This is Sahar's projection, and from 60, 180 and 300. 60, 180, 300 we get staggered forms. By 0 angle, 120 angle, 240 angle, 360 angle we get eclipsed forms. Hope you understood. Next, conformational isomerism in N-butane. That is important, especially in NEET. Conformations of ethane, conformations of butane, they are asked frequently. More questions. We are finding more questions in NEET from this topic. In stereoisomers, first stereoisomer, conformational isomer, second configurational. Configurational isomerism I will explain in next video. So next example, ethane example completed. Conformational isomerism in N-butane. N-butane, CH3, CH2, CH2 and CH3. Okay, here I am taking this carbon, 2 carbon atoms. So front carbon, and this is a rare carbon. Front carbon contain 3 hydrogen atoms, 2 hydrogen atoms, 1 methyl group and 2 hydrogen atoms. Front carbon contain 1 methyl group, 2 hydrogen atom. Rare carbon also contain this is rare carbon. Rare carbon also contain what? 1 methyl group exactly behind the methyl group of front carbon. Here hydrogen. Okay. By rotation about of 60 degrees. Carbon single bond rotation. Second carbon, third carbon. This is methyl group, like this. Methyl group CH3. First carbon, second carbon. Here third carbon, again fourth carbon. 1, 2, 3, 4. So here first carbon, second carbon, third carbon. Second and third carbons are aligned with each other, and first and fourth carbon. Second, third carbons aligned with each other, and first and fourth carbon aligned with each other, like this. Okay, we have to imagine. By the rotation about of this bond, comes here. So this one comes to here. About of which rotation? 60 degrees rotation. About of 60 degrees rotation. Then by keeping one carbon constant, front carbon constant. So here this is rare carbon. 60 degrees means methyl group comes here. Hydrogen, this one hydrogen comes here. This hydrogen comes here, like this. Okay. Next, again by 60 degrees. Again carbon single bond rotation by 60 degrees. What we get? Keep front carbon hydrogens constant, CH3, and this is hydrogen here and hydrogen here, and rare carbon. So by rotation again it comes here. So methyl group comes here behind this hydrogen comes here, okay, behind front carbon hydrogen, this hydrogen comes here. So like this. Next, again by rotation 60 degrees, carbon-carbon bond rotation by 60 degrees. What happens? See here, by this rotation, so CH3 front carbon contain one methyl group and two hydrogen. It's a rare carbon. This methyl group comes here like this, and this hydrogen comes here by the 60 degrees rotation. This hydrogen comes here. Okay, so if you see carefully, two methyl groups are opposite to each other. This is called staggered conformer. And here methyl group aligned with methyl group, this is fully eclipsed conformer, because front carbon atoms are aligned with rear carbon hydrogens are exactly behind the front carbon atoms. Thus this is fully eclipsed. This is also front carbon groups or front carbon atoms are aligned with rear carbon, but hydrogen behind methyl behind hydrogen. I will say this is partially eclipsed, not fully eclipsed. Eclipse means all are in one line. Eclipse means like this. So partially eclipsed one. That is fully eclipsed one, because methyl behind methyl, hydrogen behind hydrogen, hydrogen behind hydrogen, fully eclipsed. Hydrogen behind methyl behind hydrogen, partially eclipsed. All are far from each other, maximum separation staggered. So this is Gauche form. So there are four forms are possible: fully eclipse, Gauche form, second one, partial eclipse, third one, and staggered one, fourth form. Among the stability order is stability of N-butane. This is N-butane. Okay, which one is more stable? Staggered form is highly stable, because here torsion angle is very less, because methyl groups are very far, 180 separation, very far. That is more stable. After that, Gauche is stable because maximum separation. After that, Gauche stable. So when compared to methyl hydrogen repulsions are very stronger. That's why this is highly unstable. This is somewhat stable. Partial eclipsed form somewhat stable than fully eclipsed form. That's why 3 is more stable. 3 is more stable when compared to first one. The stability varies between conformations of N-butane. Okay, hope you understood well. So see this video once or twice, you can understand better. Thank you.